Welcome to science class. Today we are going to learn about the brief lives and spectacular deaths of high-mass stars. You owe your existence to these high-mass stars. Let's review.
In the beginning.
In the early universe, the only elements that existed were hydrogen, helium, and tiny amounts of lithium. Stars like the Sun, which are common, can only create a few more elements: carbon, oxygen, and neon. In order to have a planet Earth, we need a ton of iron. Well, a few trillion tons of it. We also need silicon and magnesium and aluminum and heavy radioactive elements to maintain a hot molten core and convective mantle. You are a product of the Earth. Life evolved on the planet out of the chemistry of atoms and molecules that have always existed on Earth. While most of you is composed of simple elements, you also need tiny amounts of sodium, calcium, chlorine, iron, molybdenum, whatever that is, and many more. We used to think that it was only in the final stages of existence for high-mass stars that these heavier elements needed to create rocky planets and eventually life could be created. Today we know a lot more. Exploding white dwarfs create over a dozen elements. Dying low-mass stars create over 3 dozen elements. Merging neutron stars create over 4 dozen heavy elements. However, in the core of medium and low-mass stars, as I said, we only get a few elements like helium, carbon, neon, and silicon. In the core of massive stars, only elements as heavy as iron can be made. This is regular nucleosynthesis. The processes that create the rest of the elements are various types of what we call explosive nucleosynthesis. More about that later. The point is, you, the Earth, almost everything you touch and feel are all literally made out of star material. Let's get started. Another quick review. All stars spend 90% of their life in the main sequence stage. All that happens in the main sequence stage is hydrogen nuclei fuse into helium nuclei. Low-mass stars can do this for 1 trillion years, medium-mass stars can do this for 10 to 12 billion years, but high-mass stars run out of fuel much faster. A star twice as massive as the Sun exhausts all of its hydrogen supply in the core in only 2 billion years. A star 8 times more massive runs out in just 100 million. The reasons why more massive stars use up all of their available fuel were discussed in the previous video if you want to check that out again. The point, again, is that even though the main sequence stage ranges in absolute time greatly between stars, it's always proportionately 90% of the star's life. And by life, I mean time spent undergoing nuclear fusion of some kind. When a star dies, whatever is left of it will continue existing for far, far longer than the time the star spent undergoing nuclear fusion. But part of the definition of a star is an object which undergoes fusion. So whatever happens after fusion stops doesn't count. The final 10% of the life of massive stars, we're talking 8 times the mass of the Sun or more, involves a complex series of different fusion layers and the most energetic and violent events possible in the universe. The reason these stars can fuse more elements and die so spectacularly is because they are more massive and achieve much greater temperatures and pressures in their core. These stars are blue because their surface temperatures reach up to 30,000 degrees Kelvin, which is nothing compared to the temperatures in their cores. At temperatures of 1 billion degrees, neon nuclei fuse into magnesium and oxygen. At 1.5 billion degrees, oxygen fuses to silicon. Between 2 and 3 billion degrees, silicon fuses into iron nuclei, which is a huge problem that we will return to soon. Like with medium-mass stars, high-mass stars also swell when hydrogen fusion in the core stops, but the swelling is much more extreme. These stars become hypergiants. VY Canis Majoris, the largest star that we know of, is 2 billion kilometers across. If it was translocated to the center of our solar system, its outer edges would go 250 million kilometers past Jupiter. In medium-mass stars, like the Sun, hydrogen fusion will continue in a layer just outside the core and can go on for about 1 billion years or so after the main sequence stage. But it's much different in high-mass stars. Towards the end of a massive star's life, it will have multiple layers outside the core where multiple different nuclei are fusing together. It's just like a giant billion-degree space onion, except for in every single way. The rate at which the star consumes its nuclear fuel while fusing other elements grows exponentially. The star may last for 100 million years, but it fuses all of its available helium nuclei in only 1 million years, all of its carbon nuclei in 1,000 years, all of its neon nuclei in 1 year, all of its oxygen nuclei in a few months, and all of its silicon nuclei in a single day. 1 day! The reason the star expands is because nuclear fusion releases energy, except for when it doesn't. When silicon nuclei fuse and become iron nuclei, energy is absorbed. This is bad news for the star. Making iron in the core is fatal. There's no going back. Very soon after the first iron nuclei are made, the star dies. It dies because the star's core has immense gravity, but now there's nothing stopping gravity from crunching the core down. Nothing, that is, except for the properties of subatomic particles themselves, but those are extremely microscopic, so a lot happens before that limit is reached. At a critical point, the core of the star begins to collapse, and I mean totally collapse, more like an implosion. The gravity of the core is so strong that the core of the star goes from several hundred kilometers across to less than 30 kilometers across in a few thousandths of a second. That core is now so contracted that it has the potential to exceed the known laws of physics. The core will either become a neutron star or a black hole. I will explain those in more detail soon. But first we have to discuss what happens to the rest of the star. The collapse of the core concentrates its mass so much that it causes its gravitational pull to magnify to a degree that I'm not even going to try to explain with numbers. But what it causes is the remaining outer layers of the star to collapse onto the core. The collapse of the rest of the star, which contains most of the mass of the star, causes, as you can imagine, enormous amounts of heating and compression. But the outer layers do not become absorbed by the collapsed core. Oh no. As the core collapsed, it created a shockwave of sorts, made out of the lightest known particles in the universe, neutrinos. Neutrinos are so tiny that a neutrino could pass through trillions of kilometers of solid lead and not bump into anything. To them, solid material is about as dense as outer space is to us. However, so many neutrinos are produced by the collapse of the core that many of them do slam into the collapsing outer layers of the star. The collapse of the outer layers of the star, which is happening at many hundreds or thousands of kilometers per second, slamming into the neutrinos, which are traveling relatively close to the speed of light, causes the star to explode. A supernova has just occurred, and the stellar material is flung away at 10% the speed of light. The supernova is so energetic that it allows for the production of heavy elements through a process called explosive nucleosynthesis. This is where many of the elements heavier than iron are produced, and why they are much more rare, because they only can be created this way. Supernovae can release more energy all at once than the star emitted over its entire 100 million year lifetime. Yeah, they release so much light and energy that from a distance of thousands of light years, we can still see them. The Crab Nebula is a remnant of a supernova 6,500 light years away, which was observed in the year 1054. Accounts indicate that this supernova was visible for 642 days during the night, but it was so bright that it could also be seen during the daytime for 23 days. Imagine this, an explosion that is so bright that it shines for hundreds of days, even from a distance of thousands of light years. Well, you can't imagine it, but it's true nevertheless. In fact, it's still glowing. Because it's 6,500 light years away, we don't see it as it truly exists in this moment of time, but as it looked 6,500 years ago. But the supernova was observed almost 1,000 years ago, and when we look at it today, we still see that it glows. This supernova, in other words, continues to illuminate the surrounding area 1,000 years later. These types of nebulae are what remain of the portion of the star outside of the core. But the really amazing things are what remains of the core. Stars between 8 to 20 times the mass of the sun become neutron stars. Sometimes you'll hear this described in terms of the mass of the core only. If the core of the star is 1.4 to 2.8 times the mass of the sun, then the core will collapse into a neutron star. Same thing, it's just whether you focus on the entire mass of the star or just the mass of its core. So what is a neutron star? Remember how I said earlier that when silicon nuclei fuse into iron, the core collapses? The cores of these stars collapse so much that there no longer are protons or electrons. The electrons, in fact, are absorbed by the protons, neutralizing them, turning them into neutrons. This is a big deal because since neutrons have no charge, they don't repel each other. Normally, the nuclei of atoms can't get anywhere near each other. This is because the electron shield around them, which is negatively charged, repels the neighboring atom's electron shield. And on the scale of atoms, the nucleus is extremely far away from the electron shield. If an atomic nuclei were the size of a marble, then its electron shield would be around 50 meters away. So under normal circumstances, one marble takes up this much space. Now imagine all of that empty space completely filled with marbles in 3 dimensions. This is what happens when electrons are absorbed by protons and the neutron star forms. The density is unimaginable. A neutron star will be very small, only about 20 kilometers across, but it has the mass of roughly 1.5 to 3 times that of the Sun. A cubic centimeter of neutron star material would weigh 400 million tons. Remember how we learned that the surface gravity of Jupiter isn't that much more than Earth because of how the planet is spread out? Well, a neutron star is so massive and so compact that the surface gravity is 100 billion times stronger than Earth's. Neutron stars are insane. But it gets even better because there are different kinds of neutron stars. Watch this. Now, this is going to be confusing, but this figure skater is not speeding up. Her rotational speed is constant. In fact, because of friction, she's actually slowing down all the time. This is known as the law of conservation of angular momentum. Let's think about it this way. A day on Earth is 24 hours. Earth is a little more than 25,000 miles in circumference. This means that Earth is spinning more than 1,000 miles per hour at the equator. But it doesn't feel like it is because Earth is so large. But imagine if you spun a basketball on your fingertip at 1,000 miles per hour. You would definitely notice that. But both objects have the same rotational speed, the same angular momentum. That's what the figure skater does. She begins with her arms far away. Her rotation looks slow, but her arms create a very large circle, and at the edge, it spins much faster than you think. When she brings her arms in and greatly decreases her radius, the number of revolutions per second she accomplishes goes up, but her speed of rotation is the same. Let's do the comparison using gears. See how the smaller gear completes many more 360-degree rotations than the large gear does? But they are spinning at exactly the same speed, because they are directly connected to each other. I bring all of this up because stars also spin. Because stars are composed of plasma, they don't spin as a whole unit. This is just starting to be understood from what I found on the internet. But we think the sun's core spins 4 times faster than its outer surface. For our sun, that would mean the core is spinning at about 8 kilometers per second. Now imagine a ball about 20 kilometers across spinning that fast. It would make a complete revolution in less than 8 seconds. But neutron stars form from much more massive stars, and their spin can be way more extreme. A neutron star can rotate hundreds of times per second. Yes, hundreds of times. Over 700 revolutions for the fastest spinning ones. This causes the gravitational fields of these objects to be trillions of times stronger than the sun's. There are 2 unique kinds of neutron stars I want to tell you a little bit about. The first are pulsars. These are neutron stars that blast radiation out from their poles, the imaginary points where they rotate around. Pulsars don't just spin in place, they also precess, which is what gyroscopes do as they spin. Earth is precessing also. If a pulsar's beam of radiation happens to point directly towards the Earth, we see them as these intense flashes of light with extremely powerful telescopes, that is, not with the naked eye. The Crab Nebula, which we looked at earlier, is illuminated by a pulsar in its center. The pulsar's energy causes the diffused material, which is well over 5 light years across, to glow. Then there are magnetars. These are neutron stars with magnetic fields up to 1,000,000,000 times stronger than the sun's. Magnetars are capable of releasing energy similar to a solar flare, but obviously much more energetic. A single magnetar flare can release more energy than the sun outputs in 250,000 years. A magnetar 50,000 light years away bombarded the Earth with X-rays, momentarily disabling some satellites and partially ionizing Earth's upper atmosphere. Its effects were more powerful than the effects of solar flares from our own sun, which is only 8 light minutes away, or over 3 billion times closer. Magnetars are scary, but luckily they are extraordinarily rare. Now, if the star has a collective mass over 20 times that of the Sun, or if its core is greater than 3 times the mass of the Sun, then when the core collapses, nothing stops it. It collapses into infinity. Its density becomes immeasurable. At least that's how I understand it, to the extent to which I do understand it, that is. This is a black hole. Black holes just don't make any sense. They have mass, but their volume is 0, hence the infinite density. So it's kind of impossible to say that a black hole is a thing, an object. It takes matter and changes it to a state where the known laws of physics can't explain it. Now, there are all kinds of things we know about black holes and what happens around them. Like I've said, this is way beyond my education, but I will share a few things about black holes with you. Why are they black? After all, they are made of the collapsed core of a star, so they should be unbelievably hot. So why don't they glow? This is because a black hole does not allow anything to escape from it. Nothing. Not light, not heat, not information, nothing. Except apparently they evaporate over time. It's called Hawking radiation. On Earth, if you throw a ball in the air, eventually it comes down. But theoretically, there's a speed you could throw it at where the ball never comes back. This is what we call escape velocity. Generally, the more massive the object, the greater its escape velocity. Black holes are so dense, and their gravity is so strong, that the speed at which an object would have to be launched from its surface to escape is greater than the speed of light. No object with mass can travel greater than or equal to the speed of light, so the black hole is black. It's not really black because color is a property of matter. It's more like it's a void. It can't be observed, so it appears empty, a pit of complete non-information, which to us looks black, I guess. You probably saw this photograph when it came out. This is the black hole in the center of galaxy M87. Earlier I said black holes have no volume, but this thing you're looking at clearly has a width. What you are actually seeing is called the Schwarzschild radius. The Schwarzschild radius is the boundary where the gravitational pull exceeds the speed of light. The gravitational field of an object extends beyond its own physical edge. That's why if you jump off of an airplane, you still fall towards the Earth. So this isn't exactly a picture of a black hole, because that's not possible. It's a picture of the space around a black hole, and a certain area can't be viewed because of what I said earlier. What you might think about black holes is they act like cosmic vortexes, sucking in material. That's not really true. Black holes don't gobble up material unless that material gets pretty close to the black hole. If the sun were compressed to a radius of just 3 kilometers across, it would become a black hole. But Earth and all other planets would just orbit around it exactly as they do today. Only if you got very close to the black hole would you fall towards it and be destroyed. Remember that gravity weakens with the distance to the center of the object. Your feet are pulled towards Earth stronger than your head when you stand up. But Earth's radius is so large, and Earth is not a black hole, so it's not noticeable. But black holes are so compacted that the difference in gravitational pull across an object's length becomes insanely exaggerated. Interestingly, this is magnified strongest in smaller black holes, because they have the smallest Schwarzschild radius. If you fell towards one of these small black holes, you would be ripped apart and sucked towards it as a stream of particles. Kind of like pulling a loose thread on a t-shirt and seeing the entire thing unwind. Scientists honestly call this phenomenon spaghettification. We have seen something similar to this happen when stars get too close to black holes. In this footage, we see a star ripped apart and destroyed as it got too close to a black hole, and the surface closest to the black hole was pulled away from the rest of the star. Almost all large, mature galaxies have what are called supermassive black holes in their centers, like the one in galaxy M87. The Milky Way contains a supermassive black hole that is 4.3 million times the mass of the Sun. It did not form from a star that big. That's impossible. It has grown in mass over billions of years as stars and random materials that have gotten too close to it have been absorbed by it, causing it to grow. There are so many other amazing facts centered around black holes, but again, I'm not the one to explain them. There's tons of content out there on this stuff, so I highly encourage you to look into it. But that concludes this video. Next time, we are going to explore galaxies. Thanks for watching.